Somewhere out there, a black hole is beating like a heart. Not metaphorically, measurably. Every few days, a distant galactic nucleus flares in X-rays, fades, and flares again on a rhythm precise enough that scientists can almost set a clock to it. Astronomers call it a quasi-periodic eruption, and it was only discovered a few years ago. Now, one particular black hole, newly awakened after decades of silence, has started pulsing longer and stronger than anything seen before, and its rhythm keeps changing in ways nobody predicted. Tonight, we listen closely to that pulse, trace it back to its discovery, and sit with a truth stranger than fiction. The universe has a heartbeat, and we only just learned to hear it. If this kind of quiet cosmic mystery is the sort of thing that helps you drift off, it would mean a great deal if you tapped like and subscribed. It costs nothing, and it truly helps this little channel keep the lights on, so more of these stories can find their way to you. Get comfortable and let your eyes rest. In 3, 2, 1, liftoff. For most of human history, and for most of scientific history as well, the black hole has stood for exactly one idea: silence. Not the mild silence of a quiet room or a still night, but something more absolute than that. A black hole is a place where light itself, the fastest and most persistent traveler the universe has ever produced, cannot find its way back out again. Whatever drifts across that final boundary, the one scientists call the event horizon, simply stops sending word home. No signal returns, no flicker escapes. For generations, when astronomers pictured a black hole in their minds, they pictured something like the deepest well ever dug into the Earth. The kind where you could drop a stone from the rim and never once hear it strike bottom. Scientists have believed some version of this for a very long time. When Albert Einstein's equations first suggested that such an object could exist back in the early 20th century, even Einstein himself found the implications difficult to fully accept. The mathematics described a place where the ordinary rules governing space and time simply broke down, a boundary beyond which nothing, not a radio signal, not visible light, not even a message broadcast with every ounce of power humanity could ever muster, would find its way back to us. For decades afterward, this was treated as a mathematical curiosity more than a real astronomical object, until slow, patient observation gradually convinced even the most skeptical scientists that these things were not just possible on paper. They were out there by the millions, scattered through galaxies, including our own. It was not until the year 2019, the very same year our story properly begins, that humanity finally caught its first direct glimpse of one of these objects. An international collaboration of scientists released the very first image ever captured of a black hole's silhouette, a dark, perfectly round shadow ringed by a faint glowing halo of infalling gas, sitting at the heart of a distant galaxy called M87. That single photograph, assembled from data gathered by telescopes scattered across the entire planet, confirmed in the most direct way possible everything theory had long predicted: total darkness at the center, and light only in the disk of doomed material still spiraling around the outside of it. It was a fitting coincidence that in that very same year, a different black hole in a very different galaxy would offer up a discovery just as startling in its own way. Though this one would not arrive as a single still photograph, it would arrive as a rhythm. That picture of silence is not wrong, it is simply incomplete. Nothing does cross back out from behind the event horizon itself. That much remains as true today as it was when the very first black hole theories were written down. But the matter still circling on the near side of that boundary, the doomed gas and dust spiraling toward a black hole in the last days or hours before it finally falls in, behaves very differently. It can glow brighter than anything else in its galaxy. It can flare with the sudden violence of a struck match. And in a small handful of galaxies scattered across the observable universe, astronomers have now confirmed something that, on first hearing, sounds almost too strange to be real. Several supermassive black holes appear to pulse, not the way a candle flickers in an open window, randomly and without pattern, but on something closer to a genuine rhythm, rising and falling again and again, hour after hour, for months at a stretch, in a manner that resembles nothing so much as breathing or a heartbeat. Before we go any further, it helps to understand why astronomers were watching this particular kind of light in the first place. The light we are describing here is not the visible light your eyes would catch if you somehow floated close enough to see it directly. It is X-ray light, the same general kind of radiation a doctor once used to look at the bones in your hand, except here it is being generated naturally by gas heated to tremendous temperatures as it swirls toward a black hole. Picture water circling the drain of an old porcelain bathtub, spinning faster and faster as it draws nearer the center, the way a figure skater spins faster the moment she pulls her arms in close to her body. Gas falling toward a black hole behaves in something like that same way, gathering into a wide, flattened disk, spinning ever faster as it spirals inward, with each layer of gas rubbing and grinding against its neighbors. That friction generates heat, and not the mild heat of a stove burner, but temperatures reaching into the millions of degrees Fahrenheit, hot enough that the gas itself begins glowing not in ordinary visible light, but in X-rays. The black hole, at the center of all this, remains exactly as silent and as dark as ever. It is the gas gathered around it, dying its slow and violent death, that does all the shouting. Earth's own atmosphere, mercifully for those of us standing on the ground, blocks X-rays from deep space almost completely before they ever reach us. That protection is wonderful for living things, but it is a genuine inconvenience for anyone hoping to study the X-ray sky, which is why astronomers who study this kind of light are forced to place their instruments in orbit, high above the interference of our own air, looking down at nothing and out at everything. This part of the story properly begins with one such instrument, and with the person who was patiently reading what it sent back to Earth. His name is Giovanni Minuti, an astrophysicist working at the Centro de Astrobiología, a research institute just outside Madrid, Spain. In the final weeks of 2018, Minuti and a small team of colleagues were not hunting for anything especially dramatic. They were simply keeping a promise to a galaxy that had already surprised them once before, a modest, forgettable little system catalogued under the plain designation GSN-069. If you have never heard of GSN-069, you are in very good company. Almost nobody had, before this story began. It carries no poetic nickname, no place in any picture book of the cosmos, nothing like the grandeur people associate with the word galaxy. It sits somewhere in the neighborhood of 250 million light-years from Earth, a distance so large it defies ordinary comprehension, and yet, in the vast accounting of the universe, that actually makes it something of a near neighbor. Many of the faint smudges filling our deepest telescope images lie billions of light-years away, from a time before our own solar system had even finished forming. GSN-069, by comparison, is practically next door. Astronomers classify it as a Seyfert galaxy, a category first described back in 1943 by the American astronomer Carl Seyfert. who noticed that a small number of otherwise unremarkable spiral galaxies had unusually bright, compact centers, a telltale sign, scientists later realized, of an active black hole steadily feeding on the gas around it. Most Seyfert galaxies simmer along quietly by black hole standards, glowing modestly and predictably, without any of the drama we are about to describe. For most of the 20th century, this particular galaxy registered as little more than a faint, forgettable point on an X-ray map, one entry among a great many others. And for a long while, that is exactly what it remained. In the final years of the Cold War, a satellite named ROSAT swept its instruments methodically across the entire sky, cataloging the X-ray brightness of tens of thousands of distant objects, one after another. It was, in its day, the most thorough X-ray map of the heavens ever assembled, a quiet, patient census of a sky most people never think to look at, since human eyes were never built to see in X-rays at all. When its gaze crossed GSN 069, the reading it carried home was almost nothing, a faint whisper of X-ray light so weak it barely rose above the surrounding noise. There was no reason, at the time, for anyone to think this galaxy was anything but ordinary. The reading went into the archives, one small entry filed alongside countless others, and the world of astronomy moved on without giving it a second thought. Then, roughly 16 years later, everything changed. Astronomers checking back in on that same patch of sky discovered that GSN 069 had brightened enormously, not by some small and forgivable margin, but by more than 240 times what that earlier survey had ever recorded. Something violent enough to transform a nearly invisible smudge into a source demanding real scientific attention had clearly taken place at the heart of that galaxy. The explanation that made the most physical sense, and the one most astronomers still favor, was almost as dramatic as the brightening itself. A star, an ordinary star perhaps not so different from our own sun, appeared to have wandered too close to the black hole waiting at the galaxy's center, and had been caught, stretched, and slowly torn apart by that black hole's gravity, in an event scientists call a tidal disruption. Picture a grape held firmly between two fingers and drawn slowly apart until its skin can no longer hold together, except here the fingers are gravity itself, endlessly patient and impossibly strong, and the grape is the outer layers of a star that never saw its fate coming. The wreckage from an encounter like that does not disappear in an instant. It can spiral inward for years afterward, feeding the black hole in a long, gradual afterglow that slowly dims as the last of the stellar debris is finally consumed. That fading afterglow is precisely what Minuti and his team expected to keep documenting when they returned their attention to GSN 069 at the close of 2018. Their instrument of choice was a spacecraft named XMM Newton, an X-ray observatory built and operated by the European Space Agency, launched into orbit in December of 1999, and still, decades later, quietly circling far above the Earth's protective blanket of air. The plan for this particular observing run was straightforward, almost routine by the standards of modern astronomy. The team wanted to track how the galaxy's X-ray brightness continued its slow decline, adding one more careful data point to the long story of a star's final undoing. For a while, the data behaved exactly as anticipated, and then it did not. Across a monitoring campaign that stretched 54 days, the instrument aboard XMM Newton began recording something that had no comfortable place anywhere in the existing science. The galaxy's X-ray brightness was not settling into the smooth, gentle decline the team had planned for. It was pulsing. Sharp, Sudden spikes of X-ray light kept rising up out of what had been, only moments before, a calm and level baseline, and just as quickly, they kept falling back down again. Picture the display on an old hospital heart monitor, the kind with a thin green line tracing a slow, even rhythm across a dark screen, until without warning the line leaps sharply upward, holds there for a stretch, and then eases back down to its resting level, only to repeat the very same motion again, a short while later, and then again, and again, through the night and into the following day. That is very close to what these astronomers found themselves watching unfold in their instruments' readout, except the machine doing the recording was orbiting far above the Earth, and the heartbeat it was tracing belonged not to any person, but to a black hole roughly 400,000 times the mass of our own Sun. That may sound enormous, and by any earthly measure it is, and yet, as black holes go, it counts as a relatively modest one, smaller than the black hole anchoring the very center of our own Milky Way, the one astronomers call Sagittarius I star, by a factor of about 10. Picture, for a moment, what such an event might actually look like if a hidden camera could somehow capture it in visible light rather than X-rays. A wide, flattened disk of glowing gas circles the black hole in near silence, gas the color of dying embers, dim and steady. Then, in the span of a single held breath, a portion of that disk brightens sharply, flaring outward with sudden ferocity, before settling back to its slow ember glow, as though some hidden hand had briefly stoked a fire and then let it die back down again. No camera has ever actually filmed this, of course. Everything we know about it comes from an X-ray detector counting individual particles of light, arriving after a journey of 250 million light-years across empty space, translating an invisible signal into the rising and falling brightness readings scientists study on their screens. But the picture those numbers describe, once you sit with it, is almost cinematic in its drama, unfolding again and again in the quiet, dark at the center of a galaxy nobody had ever paid much attention to before. The rhythm itself, once the team had time to study it properly, turned out to be almost unbelievably tidy. Roughly every 9 hours, without fail, a fresh burst of X-ray light rose up out of the galaxy's core. Each burst lasted a little over 1 hour before subsiding, and at its peak, the brightness did not simply increase, it multiplied, climbing as much as 100 times brighter than the calm baseline glow the galaxy had shown only shortly before. Then, like a wave drawing back from a shoreline, the brightness eased downward again, the galaxy fell quiet, and the whole pattern began building steadily toward its next release. Over and over, through 54 unbroken days and nights, this small and previously unremarkable galaxy kept doing the same extraordinary thing again and again, with a regularity that felt less like the behavior of a distant, indifferent object and more like something with a genuine pulse. Naturally, the team did not simply accept a reading this strange on faith. This is, in many ways, the least glamorous but most essential part of any real scientific discovery, the long, careful process of trying every reasonable way to prove yourself wrong before allowing yourself to believe you might actually be right. Instruments drift, detectors age. Cosmic rays occasionally strike a sensor in ways that can mimic a genuine signal. Minuti's team ruled out each of these possibilities in turn, patiently and methodically, the way a careful homeowner checks every window and door twice before finally believing the house really is secure for the night. They checked their instruments' calibration, They compared the pattern against everything already known about how X-ray detectors can occasionally misbehave, and they watched the rhythm repeat itself again and again across those 54 days until any lingering doubt about a technical glitch became impossible to sustain. The pattern was real. It kept happening whether anyone was watching that particular hour or not, faithfully, on its own schedule, indifferent to whether a human being happened to be paying attention. It is worth pausing here, in the gentle quiet of this story, to sit for a moment with how strange that really is. A black hole, after all, is supposed to represent a kind of ultimate consistency, a slow, one-directional consumption of anything that strays too close, with no obvious reason to behave, one way in 1 hour, and an entirely different way 9 hours later. And yet here was careful, repeated, rigorously measured evidence that something in the immediate surroundings of this particular black hole was operating on a genuine rhythm, a private schedule of its own, playing out with a regularity that felt far closer to a living thing than to the cold, silent picture generations of scientists had grown used to imagining. Astronomers do not use a word like rhythm carelessly, and in describing what they had found, Minuti's team chose their language with real precision. The bursts were not perfectly identical from one to the next, not tick for tick, the way a mechanical clock advances. Careful study of the timing revealed a subtle alternating pattern folded into that 9-hour cycle, with some gaps between bursts running a touch longer than others, and some a touch shorter, before the whole rhythm settled back toward its broader 9-hour average. This distinction matters, and it is part of why scientists ultimately reached for the word quasi-periodic to describe what they were observing, rather than simply periodic. A period, in the strict sense scientists usually mean by that word, repeats with the same precision every single time, the way the second hand of a well-kept clock advances without ever varying. A quasi-period is gentler than that, closer to the rhythm of waves rolling onto a beach, where no two waves arrive at exactly the same interval as the one before, and yet none of them ever strays far from the underlying pattern either. If you have ever stood at the rim of Yellowstone National Park and watched the geyser called Old Faithful do its work, you already understand this kind of rhythm in your bones. Old Faithful does not erupt at the exact same interval every single time. Sometimes the wait between eruptions runs closer to an hour and a half, other times nearer to 2 hours, and generations of patient visitors have learned to expect a window rather than a precise appointment. And yet nobody would ever call Old Faithful random. It earned its famous name precisely because, window or no window, it always comes through, again and again, on a rhythm reliable enough to build a national tradition around. The black hole, at the heart of GSN 069, was doing something remarkably similar, erupting not steam and water into the sky above a forest, but X-ray light into the darkness of space, on a schedule dependable enough to shape an entire scientific investigation, even though no two intervals ever matched precisely. The word eruption itself is, in fact, a deliberate choice, borrowed knowingly from the language of geology, rather than the more clinical vocabulary astronomers might otherwise reach for. A flare suggests something brief and almost accidental, gone as quickly as it appears. An eruption suggests pressure building steadily beneath a calm surface until it finally releases, only to begin building all over again. That is precisely the behavior scientists were describing. Whether the true cause turned out to be a distant companion grazing a disk of gas, or some instability brewing within the disk itself, something was gathering, again and again, until it could no longer be contained. And then it let go, in a burst of light traveling outward across 250 million light-years of silent space, until, eventually, it found its way into a spacecraft's waiting detector. When this discovery was finally published in the year 2019 in the pages of the scientific journal Nature, it did far more than add one more curious galaxy to the astronomical record. It introduced an entirely new category of behavior for scientists to study, one with no comfortable precedent anywhere in what astronomers already understood about black holes and the disks of glowing material that so often surround them. Until that point, the general assumption had been a peaceful one. The disk of hot gas circling a feeding black hole was thought to evolve slowly and gradually, brightening or dimming over months or years as conditions shifted, never in sudden, repeating spikes measured in mere hours. GSN 069 broke that assumption cleanly in two. Something down there was behaving on a schedule, and nobody yet had a fully settled explanation for why. News of the discovery rippled quickly through observatories and university departments around the world. Scientists who had spent entire careers studying how black holes feed found themselves staring at this new data with a mixture of excitement and genuine unease, the particular feeling that comes from watching a long-settled question reopen itself without warning. Conferences that had already been scheduled months in advance suddenly made room on their programs for hastily prepared talks about this strange, ticking galaxy. Researchers who had never given GSN 069 a second thought began combing back through their own old archives, wondering whether they, too, might already be sitting on a similar rhythm, buried somewhere in data they had collected years earlier, and simply never thought to examine this particular way. Minuyuti and his colleagues were honest in their published work about the limits of what they actually knew. What they offered was not a solved mystery, but a careful, reasoned possibility, one among others still being weighed at the time. Perhaps, they suggested, the black hole was not behaving strangely all on its own. Perhaps some second, much smaller object was involved, maybe the compressed remnant of a star that had already met its end long ago, or some other compact companion, tracing a tight, repeating orbit close around the black hole. How close, exactly? Close enough that if you shrank the black hole down to the size of our own sun and set this hypothetical companion on that same tight loop at matching scale, it would be racing around far tighter than Mercury ever keeps to the real sun, completing an entire circuit in a matter of hours rather than months, an object living dangerously near the edge of no return, threading the same narrow path again and again without ever quite crossing it. On each pass, this second object might be grazing through, or otherwise disturbing, the thin disk of superheated gas that surrounds the black hole, rather the way a ring surrounds certain planets. Picture a flat stone skipped across the still surface of a pond, touching down, sending out a burst of ripples, lifting briefly free of the water, and touching down again a little farther along. Or picture a comet on a long, looping orbit, swinging in close to a star, feeling the sudden heat and pressure of that near approach, and then swinging back out again into the calm and cold of open space, only to repeat the same close pass on its next return. Something, the researchers proposed, might be doing very much the same thing here, brushing against the black hole's disk again and again on a tight, repeating loop, and each brush might be enough to release the very burst of X-ray light their telescope kept recording. It was not, however, the only idea on the table. Other researchers wondered whether the black hole needed a second object at all, or whether the disk of gas itself, left entirely alone, might simply be unstable under certain conditions, prone to its own kind of internal shudder, capable of producing a similar rising and falling brightness without any outside interference whatsoever. Both explanations remained live possibilities as this story was first being written, and settling between them, or perhaps discovering some third answer nobody had yet proposed, would take years of careful work still to come. It is, even now, an elegant idea, and it remains one of the most seriously considered explanations for what these rhythms might represent. But Minuti and his team were careful never to present it as the final word, and it was not meant as one. It was an opening question, offered honestly as a leading possibility among others still being tested in a field of study that was, at that point, barely a few months old. Nobody yet knew whether GSN 069 was some kind of singular cosmic fluke, one strange galaxy behaving in a way no other black hole ever would again, or whether it was instead the very first confirmed example of something quietly common throughout the universe, ticking away unnoticed in countless other galaxies that nobody had yet thought to watch closely enough to catch in the act. That question was not destined to sit unanswered for long. Word of this discovery moved quickly through the small community of astronomers who spend their careers studying the X-ray sky and telescopes across the world, and in orbit high above it, began turning their attention toward other quiet, unassuming galaxies, the kind that had never drawn much notice before. Archives that had sat untouched for years were suddenly worth a second look. Old observations, once filed away as unremarkable, were pulled back out and studied line by line, in the hope that some other quiet galaxy might already be holding the same secret GSN 069 had just given up. Scientists found themselves wondering, with a kind of hushed anticipation that is rare even in a field built on patience, whether this same strange and steady heartbeat, first heard coming from one small and forgettable galaxy, might already be ticking away somewhere else entirely, waiting patiently in the dark for someone, finally, to listen closely enough to notice. That hope did not go unanswered for long, and it turned out astronomers did not have to wait years to find out whether the very first discovery had been a fluke. Astronomers searching for a second example of this same strange rhythm are a little like birdwatchers who have just spotted an unusual species for the very first time, out at the edge of a familiar marsh where nobody expected anything unusual at all, a sighting exciting enough to mention to colleagues, but not yet solid enough to stake a reputation on. One sighting alone, however carefully documented, always leaves a nagging question hanging in the air. Was it truly a new kind of bird, or simply a familiar one behaving oddly on an unusual afternoon? Only a second sighting, then a third, spotted by other patient observers in other places entirely, can settle the matter and earn a new entry in the field guide. Astronomers studying the sky's X-ray light were about to get exactly that kind of confirmation, and the story of how it arrived turned out to be almost as remarkable as the discovery itself. The second confirmed heartbeat of this kind was found in a galaxy catalogued as RxJ 130.1.9 plus 2747, an edge-on spiral galaxy, meaning one we happen to view from the side rather than face on, so that its disk appears to us as a thin, glowing line rather than a full spiral. A team led by the astronomer Margherita Giustini, working at the very same research institute outside Madrid where the first discovery in this story had been made, took a fresh, careful look at this galaxy, using new observations gathered over 2 nights in the spring of 2019. That 2 researchers, working out of the same modest institute, would go on to confirm both the first and second examples of this behavior was, by most accounts, simply a matter of proximity and curiosity rather than coincidence. Colleagues down the same hallway, comparing notes on a discovery still fresh enough that almost nobody else in the field had thought to go looking yet. What Giustini's team found in that new data was unmistakable. Sharp, rhythmic flares of X-ray light, each one lasting about half an hour, rising 100-fold above the galaxy's normal quiet glow before fading away again, only to repeat a short while later. Word of a second confirmed example spread quickly among astronomers who had spent the months since the very first discovery wondering whether that first galaxy might turn out to be entirely alone in its behavior. But it was what happened next, once researchers went looking back through the archives, that turned this into such a striking story. This particular galaxy had actually been observed several times before, by several completely different telescopes, stretching back decades, each observation made for an entirely unrelated reason. An earlier orbiting X-ray observatory happened to glimpse it all the way back in 1985, while its instruments were really pointed toward a distant, well-known cluster of galaxies nearby, catching this one modest system almost as an afterthought sitting at the edge of the frame, hardly worth a second glance at the time. Another spacecraft studied it again in 1991 during a broad survey of the X-ray sky that had no particular interest in this one small galaxy specifically. One entry among thousands collected that year. The XMM Newton spacecraft observed it directly in the year 2000, gathering data that would eventually prove decisive, and Chandra took its own careful look 9 years later, in 2009, adding yet another unwitting witness to the pile. Every single one of these 4 observations, spanning the better part of 35 years, and 4 entirely different spacecraft, built by different countries for different purposes, had captured hints of the very same rapid flickering, brief, unexplained jumps in brightness that nobody at the time had any framework to make sense of. They simply did not yet know what they were looking at, because nobody yet knew that anything like this could exist at all. It is a little like discovering an old home movie reel tucked away in an attic for decades, only to finally thread it through a projector and realize it had captured something remarkable all along, something nobody watching it at the time had known enough to notice or name. Once Giustini's team re-examined that old 2000 archival data side by side with the fresh 2019 observations, comparing one set of flickering light curves against the other, the pattern became impossible to miss. This galaxy had been quietly pulsing for at least 35 years, and quite possibly much longer than that, waiting patiently across 4 separate decades for someone to finally recognize the rhythm for what it was. Every prior astronomer who had ever pointed a telescope in its direction had, without knowing it, already been collecting evidence of the very same phenomenon now being celebrated as a fresh discovery. The rhythm itself, once properly measured, told researchers something new and useful. Unlike the tidy, dependable 9-hour heartbeat described earlier in this story, this second galaxy's eruptions arrived far less predictably, with the gap between one burst and the next stretching anywhere from roughly 3.5 hours to just over 5.5 hours across the handful of eruptions captured in that 2019 observation. If the first heartbeat felt like a steady, dependable pulse This second one felt more like the pulse of someone catching their breath after a long climb, quicker in places, slower in others, never quite settling into a single fixed interval the way the very first discovery had. The black hole responsible for it was estimated at somewhere between 1 million and 3 million times the mass of our own Sun, modestly larger than the very first, but still comfortably within the same general family of relatively small, unassuming black holes. Two confirmed examples now existed, discovered independently, years apart, behaving in recognizably similar ways despite their individual differences. This mattered more than it might first appear. A single strange result in science, however carefully measured, always carries the nagging possibility of being some kind of one-off accident, an instrument quirk, a coincidence, a fluke of timing nobody could rule out entirely. A second, independent confirmation, found in an entirely different galaxy by an entirely different team studying an unrelated question, closes off nearly all of those quieter doubts at once. The bird, so to speak, had been sighted twice, and the field guide finally had a second entry to compare against the first. It would not stop at twice. In the summer of 2019, a joint German and Russian mission called Eurosita launched into space aboard a spacecraft named Spectra RG, carrying with it an entirely different way of hunting for this kind of behavior. Where the two discoveries described so far had each come from astronomers, pointing a telescope carefully at one particular target and watching closely, sometimes returning to old archives only after the fact. Eurosita was built to do something far broader from the very start, circling far from Earth and slowly scanning the entire sky, again and again, cataloging every X-ray source bright enough to notice, rather than focusing on any single galaxy at all. Over the following years, this single mission would go on to catalog more X-ray sources across the sky than every previous X-ray survey combined, sweeping past millions of galaxies in the course of its work. The difference is a little like searching for a lost object by checking one drawer at a time, room by room, versus finally getting hold of a light bright enough to sweep across an entire house in a single pass, missing nothing along the way. Within its very first years of operation, this systematic approach turned up exactly what astronomers had hoped for. More examples of the same rhythmic pulsing, found not by chance or by painstaking follow-up of a single suspicious source, but simply by patiently sifting through everything the whole sky had to offer, one methodical pass at a time. Two of these newly discovered sources illustrated just how varied this family of objects could be, and both were found in galaxies that had never before drawn any special attention from astronomers. Ordinary-looking systems, flagged only because the survey happened to sweep across them at the right moment. One of them erupted every 18.5 hours, with each individual burst lasting a little over 7.5 hours, a slow, patient rhythm compared to anything catalogued before it. Its neighbor, in the very same survey, did almost the opposite, erupting every 2.5 hours, with bursts lasting barely half an hour each, a quick, urgent little pulse by comparison, several times faster than any of its relatives. Between the steady 9-hour rhythm of the very first discovery, the looser, catch-your-breath irregularity of the second, and now this pair sitting at opposite ends of the spectrum entirely, one slow and patient, one fast and clipped, astronomers began to appreciate just how much variety this newly recognized family of behavior could actually contain. A few more examples turned up in the years that followed, found through this same systematic survey, each with its own particular timing somewhere along that spectrum, confirming that this was not a narrow, single pattern at all, but a genuine range of related behavior, the way one family of birds might include members with calls ranging from a slow, low warble to a rapid, chattering trill, all clearly related, none of them quite identical. The community of scientists devoted to studying this phenomenon remained, through all of this, remarkably small and close-knit, the kind of field where a handful of research groups scattered across a few countries kept in close, regular contact, comparing notes and sharing data almost as soon as it came in, well aware that any one of them might be the next to stumble across another example simply by looking in the right patch of sky at the right time. A pattern beyond the timing itself was also becoming clear the more of these galaxies astronomers found. Every one of them, without exception, turned out to be a relatively small, unassuming system, often what astronomers call a dwarf galaxy, containing only a modest population of stars compared to a large galaxy like our own. And every black hole discovered at the center of one of these galaxies fell into roughly the same modest weight class, somewhere between 100,000 and a few million times the mass of the Sun, small by the standards of the largest black holes known to science. There was something quietly fitting about this pattern, once researchers had time to notice it clearly. None of these discoveries were coming from the grand, famous galaxies that fill astronomy textbooks and observatory brochures. They were coming from small, overlooked places, the kind of galaxy nobody would have thought to point a telescope at for any other reason. In much the same way, some of the most remarkable turns in human history began not in a great capital city, but in some small, unassuming town that nobody outside it had ever paid much attention to before. Researchers have offered a reasonably grounded explanation for why this pattern keeps holding. A smaller black hole demands a smaller, tighter disk of surrounding gas to match it, and anything orbiting close to that disk, whether a stray star or a clump of leftover debris, has a proportionally much larger effect on a compact disk than the same object would have on the sprawling, much larger disk that circles a giant black hole. In effect, the smaller the black hole, the more dramatically a single disturbance can shake its surroundings, which may be exactly why this rhythmic behavior keeps turning up around modest black holes and almost never around the largest ones known to science. Researchers also notice something about how much of the time each of these black holes actually spent erupting versus resting quietly in between. Across the family as a whole, the active bursts themselves typically occupied somewhere between 1/10 and 1/5 of the total time, meaning that for every hour spent in the middle of an eruption, a black hole of this kind generally spent somewhere between 4 and 9 hours resting quietly in its more familiar, subdued glow. Far more of each cycle, in other words, was spent in quiet recovery than in dramatic release, a detail that would later prove useful for comparing one source against another. Dwarf galaxies of the kind hosting every one of these black holes carry their own separate scientific importance, well beyond this particular story. They are thought to preserve conditions closer to the universe's early history than large galaxies like our own, which have spent billions of years growing through repeated mergers and makeovers. A black hole, discovered pulsing at the center of one of these smaller, less disturbed systems, offers scientists an unusually clean laboratory, free from much of the messy history that complicates study of black holes in larger, more evolved galaxies. One question, though, remains stubbornly open through all of these early discoveries, one that would keep researchers occupied for years to come. Where did the material producing these eruptions actually come from in the first place? And why would a disk capable of this kind of rhythm exist around a black hole at all? Scientists had already proposed for the very first source described earlier in this story that some smaller object might be grazing repeatedly through the disk of gas surrounding the black hole, but that idea alone did not explain where such a disk or such an object originally came from. One appealing possibility, discussed since almost the very beginning of this story, pointed back to the same violent event described earlier, a star wandering too close to a black hole and being torn apart. If the leftover debris from a disruption like that settled into a disk around the black hole, perhaps that freshly formed disk was exactly the kind of stage this rhythmic behavior needed in order to play out. For years, this remained an appealing idea without direct proof, a plausible connection nobody had yet caught in the act of actually happening. Confirming a connection like this required something rare in astronomy, a single galaxy watched closely enough, for long enough, to catch both halves of the story in the act. Most tidal disruptions are studied intensely for the first few months after they are spotted, while the destroyed star's remains are still bright enough in visible light to hold astronomers' attention, and then quietly set aside as the flare fades, and telescope time gets allocated to newer, brighter events elsewhere. Very few disrupted galaxies ever get checked again in X-ray light years later, largely because there was, for a long time, no particular reason to expect anything more to find. That changed with a galaxy known by its transient designation, a T2019 QIZ, first spotted by an automated sky survey in September of 2019, as a star was being torn apart by the black hole at its galaxy's center, a textbook example of a tidal disruption, studied closely at the time using ordinary visible light by astronomers who, quite reasonably, assumed they were watching a single, self-contained event with a beginning, a middle, and an end. Nobody watching that disruption unfold in 2019 had any reason yet to expect what would happen years later. Then, astronomers checking back in on this same galaxy found something extraordinary. A brief flare had already been glimpsed by Chandra in December of 2023, and when researchers followed up more thoroughly in the early months of 2024 using NICA, the Swift Observatory, and a fourth telescope called AstroSat, working together in careful sequence, the same rhythmic eruptions described throughout this story turned out to be rising steadily from the galaxy's center. 9 of them were captured in careful detail, arriving on average every 48 hours, with each individual burst lasting roughly 8 to 10 hours. The whole sequence unfolding with a consistent shape each time, a fast rise followed by a slower, more gradual fade. The star had been destroyed years earlier. The rhythmic heartbeat had only begun afterward, arriving the way an echo sometimes reaches the far end of a canyon, only long after the shout that caused it has already faded from memory. This discovery mattered enormously, because it finally gave scientists something they had lacked through all the earlier cataloging: a single galaxy where both halves of the story, the star's destruction and the rhythmic aftermath, had each been directly observed rather than merely inferred from indirect clues. It confirmed that at least some of these eruptions truly could trace their origin back to a disrupted star, exactly as the leading idea had proposed for years without proof. The result was published in the same year it was confirmed, drawing swift attention from across the small community of researchers who had spent years searching for exactly this kind of direct link without ever quite catching it in the act before. A second, similar case turned up not long afterward, also found through the Erosita survey a different tidal disruption first identified in the second half of 2019, roughly around the same time as the disruption described above, though in a completely separate galaxy on the opposite side of the sky. Follow-up observations of this second disrupted galaxy, spread out over the following year and a half, caught brief flaring episodes, lasting less than half a day, and standing out sharply against the galaxy's otherwise quiet glow. Hints of the same rhythmic behavior playing out on a shorter, less complete record than the first confirmed case. The gap between successive flares in this second galaxy could only be pinned down loosely, somewhere between about 1 day and a little over 1 day, since long stretches passed between observations with no flare caught at all, leaving researchers uncertain whether the rhythm had simply gone quiet for a time, or whether their instruments had merely missed it between visits. Even with that uncertainty, the timing and behavior lined up closely enough with the first confirmed case that most researchers studying it treated the connection as a second, if slightly less certain, piece of supporting evidence. Even so, researchers were careful not to overstate what these two cases meant for every source in the growing catalogue. 2 galaxies confirmed to follow this exact sequence: tidal disruption first, rhythmic eruptions, years later, did not prove that every example of this behavior shared the same origin. The very first heartbeat described earlier in this story, along with several of the others catalogued since, still showed no direct evidence of ever having suffered a disruption at all. No earlier flare in the historical record, no telltale decline in brightness, matching the aftermath of a star's destruction. Whatever was happening at their centers appeared to be arising some other way entirely, perhaps through nothing more dramatic than an ordinary disk of gas around an ordinary feeding black hole, occasionally becoming unstable on its own, with no disrupted star required to set the stage at all. This left, and still leaves, 2 serious possibilities on the table for how any individual example of this rhythm might arise. Possibilities that researchers continue actively debating at conferences and in published papers to this day, neither one yet able to claim a clear, decisive victory over the other. Researchers examining the whole growing family of sources found themselves circling the same fundamental question again and again, like a jury that keeps hearing new witnesses without ever quite reaching a unanimous verdict. One possibility holds that a second, smaller object, perhaps the compressed remnant of a star, or in some cases perhaps debris left directly behind by a disruption, orbits tightly around the black hole and periodically grazes through the surrounding disk of gas, triggering each burst the way a skipping stone sends out ripples with every touch against the water. The other possibility needs no second object at all, holding instead that the disk of gas itself, under the right conditions, becomes unstable on its own, swelling and thinning in a repeating cycle that produces the same rhythmic brightening without any outside interference whatsoever. Different sources in this growing catalogue seem to favor different explanations depending on their particular circumstances, and in more than one case, researchers studying the very same galaxy argued for entirely different mechanisms without ever quite reaching agreement, each side pointing to real, careful measurements that simply did not point toward the same conclusion, publishing competing papers within months of one another, each confident in its own reading of the same underlying data. Some pointed to the way certain sources showed brightness rising and falling in a shape too smooth and symmetric to easily fit a sudden collision, favoring the disk instability picture. Others pointed to sources whose recurrence times shifted gradually in ways that matched the slow widening of an orbit far better than any process happening within the disk alone. Still others noted that the amplitude and shape of individual bursts sometimes changed subtly from one eruption to the next, in ways that neither simple picture on its own fully predicted, leaving room for the possibility that some combination of both mechanisms, or something not yet proposed at all, might ultimately be needed to explain the full range of behavior observed across the family. Neither side had yet produced evidence strong enough to settle the matter for the family as a whole, and it remained entirely possible that both mechanisms were real, simply operating in different galaxies under different conditions. If anything, each new source added to the catalogue seemed to deepen the puzzle rather than simplify it, introducing its own small wrinkle that did not quite match the pattern established by whichever galaxy had been studied just before it. Astronomers accustomed to fields where one solid discovery tends to settle a long-standing question found this particular corner of the sky unusually resistant to easy answers. Every fresh data set complicating the picture just as often as it clarified it. What had, only a few years earlier, been a single strange discovery from one modest galaxy had grown by patient cataloging, careful archival digging stretching back decades, and a newly launched sky survey working around the clock, into a small but genuine family of related objects. By the count researchers kept as new candidates continued arriving, the confirmed and strongly suspected examples numbered close to a dozen, a small enough collection that specialists studying this phenomenon could still, without much trouble, name every single one from memory, and yet large enough that nobody could any longer dismiss the very first discovery as some strange isolated fluke. Each new addition to that short list confirmed that the very first heartbeat had been no fluke at all, and each brought its own small variation on the theme, its own particular recurrence time, its own particular history, its own particular hint about which of the two competing explanations might be closer to the truth in that one specific case. Every single member of this family shared one comforting trait in common. Each galaxy involved had already been known to astronomers in some form or another, sometimes for decades, its black hole already confirmed to exist long before anyone caught it pulsing this particular way. Scientists had begun, quite reasonably, to feel they understood the general shape of this new phenomenon, a rare but genuine behavior belonging to black holes that had already settled long ago into their own quiet routine of feeding. That comfortable assumption, built patiently over several years of careful cataloging, was about to be tested by a discovery unlike anything gathered so far, involving a black hole that appeared, by every measurement scientists could bring to bear, to still be finding its very first rhythm in real time, right in front of the instruments watching it happen. By the time astronomers had spent a few years cataloging this small, strange family of pulsing black holes, a pattern of sorts had begun to emerge. However tentative and however carefully hedged, every single source found this way up to that point shared one crucial trait. Each galaxy involved was already known, already catalogued, its black hole already confirmed and quietly present for as long as anyone had been watching it. These were, in every case, black holes that had settled long ago into their slow, steady routine of feeding, only now revealing a hidden rhythm within that routine, a rhythm that, once measured, tended to stay put. Then came a discovery that broke this comfortable pattern entirely, involving a black hole that appeared, by every measurement scientists could bring to bear, to have only recently woken up and to still be finding its rhythm even as astronomers watched it happen, its heartbeat changing shape right in front of their instruments, within a stretch of years, short enough for any one of us to have lived through it ourselves. The galaxy, at the center of this next chapter, carries a name built almost entirely from coordinates rather than any sense of poetry. SDSS 1335 plus 0728. A string of letters and numbers describing exactly where in the sky to point a telescope. In the direction of the constellation Virgo, roughly 300 million light-years from Earth, a distance that places it well beyond our own local neighborhood of galaxies, out among the countless ordinary-looking systems that fill the deeper reaches of the night sky. That distance is worth sitting with for a moment. The light reaching our telescopes from this galaxy, tonight first, began its journey roughly 300 million years ago, long before the first dinosaurs ever walked the Earth, back when only the earliest reptiles were beginning to creep across a much younger planet. Whatever we are seeing happen at the center of that galaxy did not happen recently at all, at least not from that galaxy's own point of view. It happened an unimaginably long time ago, and its light is only now, after all this time, finally arriving here to be read. For 2 full decades of our own more recent history, this galaxy gave astronomers no reason whatsoever to look twice. It sat quietly in the survey archives, one small, faint, entirely unremarkable galaxy among the millions charted and filed away by large sky surveys over the years, its center dark and calm, showing none of the telltale brightness that would suggest an actively feeding black hole at its heart. Whatever was waiting at the center of this galaxy, it had, as far as anyone on Earth could tell, been waiting quietly for a very long time. Then, in December of 2019, something changed. An automated sky-watching system called the Zwicky Transient Facility, a wide-field camera operating at Palomar Observatory in the mountains of Southern California, scans huge portions of the sky, night after night, searching for anything that brightens or fades unexpectedly, comparing each new image against everything it has recorded before, and flagging whatever looks different. On this particular night, it flagged this one small, previously unremarkable galaxy as suddenly, unmistakably growing brighter. The system logged the event under its own internal tracking code, a long string of letters and numbers used to keep its automated alerts organized, and buried inside that string was a short fragment that happened to read rather like a name. Astronomers studying the galaxy picked up on that fragment and began calling their new discovery Ansky, and the nickname has stuck ever since, used far more often now than the galaxy's own official designation ever is. What Ansky's light was doing, once astronomers turned their attention toward it, resembled the behavior scientists associate with an active galactic nucleus, meaning a galaxy whose central black hole has begun visibly feeding, releasing extra light as gas swirls inward toward it. But there was something genuinely strange about this particular case, and the distinction mattered a great deal to the researchers studying it. Most active galactic nuclei have clearly been active for a very long time, their behavior steady and familiar to anyone who has studied them for years, the way a long-running furnace hums along at a familiar, dependable temperature once it has been burning for decades. This galaxy showed no such history whatsoever. For 20 years, nothing. Then, seemingly out of nowhere, a black hole apparently switching itself on, the way an old furnace that has sat cold and unused for years might slowly begin to catch and roar to life once someone finally strikes a match beneath it. Astronomers who studied the earliest data honestly acknowledged that two very different explanations were still on the table, and the choice between them was no small matter. Either this was a supermassive black hole igniting for the very first time in living memory, waking from a long dormancy after who knows how many years of quiet, which would mean scientists were watching a black hole essentially come of age in real time, or it was something else almost as rare, an unusually long, unusually faint tidal disruption event, the slow, drawn-out aftermath of a star being consumed, playing out far more gradually than any such event previously observed. Telling these two possibilities apart mattered, because each one would say something entirely different about how common newly waking black holes might actually be throughout the universe, and about how often the quiet, settled-looking galaxies that fill our night sky might secretly be hiding a black hole on the verge of switching on. Time and continued watching would be needed to tell the two apart. Over the years that followed, the galaxy's light kept climbing steadily across several different colors of the spectrum, each one telling researchers something slightly different about what was happening at its center. By 2021, its ultraviolet brightness had grown to roughly 4 times what it had been before this whole episode began. By June of 2022, its mid-infrared brightness, the kind of light most closely tied to warm dust surrounding a feeding black hole, had more than doubled again on top of that. Every measurement kept pointing the same direction. Something at the center of this galaxy was steadily, patiently waking up. That continued watching lasted years, not weeks, and it required a small fleet of instruments working in patient succession. Astronomers checked archived observations from a German-led X-ray survey called Erosita, covering the period from 2020 through 2023, and found nothing. No X-ray light at all coming from the galaxy's center during that entire stretch. A separate follow-up campaign using NASA's Swift Observatory, running from the middle of 2021 through the middle of 2023, likewise came up entirely empty in X-rays. Even as the galaxy continued brightening steadily in visible and infrared light the whole time, it is worth pausing on that patience for a moment. For roughly 2 years, scientists kept quietly checking on a galaxy that was clearly changing in every other way they could measure, and kept finding, again and again, that whatever was happening at its center still had no X-ray voice at all, like watching a house with its lights slowly coming on room by room while the front door stays firmly shut. Whatever process was unfolding in that galaxy's core, it was, for years, keeping that particular kind of light entirely to itself. Then, in February of 2024, that silence finally broke. Soft X-ray emission appeared for the first time, and a dedicated observation using NASA's Chandra X-ray Observatory confirmed the light was genuinely coming from the galaxy's very center, and not from some unrelated foreground object merely happening to sit along the same line of sight. A team of astronomers, led by Lorena Hernandez Garcia, moved quickly once the X-rays appeared, arranging for one of NASA's X-ray telescopes, an instrument called NISA, mounted to the outside of the International Space Station, to begin a sustained, high-cadence watch. Between the middle of May and the end of July that year, NISA captured a snapshot of the galaxy roughly 16 times every single day, timed to the station's own orbit around the Earth, an orbit so fast that the station circles the entire planet in about 90 minutes, meaning the astronauts, living and working aboard it, watch a new sunrise or sunset arrive roughly every 45 minutes, day and night blurring together in a rhythm all their own, High above the very galaxy, their borrowed instrument was quietly studying below. What that intensive summer of watching revealed left little doubt. Ansky was erupting in the same rhythmic, quasi-periodic fashion described earlier in this story, bursts of X-ray light rising and falling on a genuine, repeating cycle. But this was no ordinary example of the phenomenon. Each individual burst lasted roughly 1.5 days, considerably longer than anything recorded before, and the bursts arrived peak to peak, meaning measuring from the height of one burst to the height of the very next one, roughly every 4.5 days, with groups of about 5 eruptions in a row forming a longer, gentler cycle stretching across approximately 25 days, much like fireworks fired off in a rapid burst of 5, before the display pauses briefly and the crowd waits for the next sequence to begin. Researchers studying this pattern even gave these clusters of 5 their own working name, calling each group a cascade, since one eruption seemed to tumble into the next before the whole sequence paused and gathered itself for another round, only to begin building toward the next cascade all over again. When astronomers compared these numbers against every previously known example of this phenomenon, Ansky came out on top by a wide margin. Its bursts lasted roughly 10 times longer than typical, shone roughly 10 times brighter at their peak, and released as much as 100 times more total energy with each eruption than the more modest sources described earlier in this story. 3 dedicated observations using the XMM Newton spacecraft, taken in the final days of June and on the first day of July that year, caught something else worth noting as well: a steady, quiet glow from the disk of gas surrounding the black hole, even in the gaps between eruptions. This quiet, continuous glow mattered a great deal to researchers, since it confirmed the disk itself persisted the entire time, with the eruptions layered on top of it, like a series of small fires flaring briefly along the edge of a much larger bed of coals that never fully goes out. The eruptions, in other words, were not the whole story. They were dramatic interruptions to a steadier, quieter process running underneath them the entire time. The black hole responsible for all of this was estimated, based on the properties of its host galaxy, at roughly 1 million times the mass of our own Sun, making it about 2.5 times heavier than the modest black hole whose 9-hour heartbeat opened this story. And yet still, by the standards of the largest black holes known to science, a relatively small and unassuming one, sitting comfortably within the same general size range as every other source of this kind studied so far, all of them modest by cosmic standards, all of them tucked into galaxies that, until each was studied closely, had seemed to hold nothing remarkable at their centers at all. When the discovery was formally published in the year 2025 in the pages of the journal Nature Astronomy, it did more than add an especially dramatic new entry to a growing catalogue. It fundamentally broadened what scientists understood about how this kind of rhythmic eruption could arise in the first place. Every earlier confirmed example had involved a black hole that was already comfortably settled, its surrounding disk long since mature, shaped and smoothed by years or decades of steady feeding, the way a river carves clean, settled banks after centuries of following the same course. Ansky was doing something else entirely, producing this same dramatic rhythm from a disk that was still actively forming, still finding its shape, more like floodwater cutting a brand new channel through ground that had never carried a river before, the banks still loose and shifting rather than fixed. A star did not necessarily need to be captured and destroyed to set a stage like this one. A black hole simply switching on, absorbing gas for the first time in decades, appeared entirely capable of producing the same kind of pulsing heartbeat entirely on its own. Once word of this spread through the astronomical community, other research teams began quietly pulling their own old survey archives back out, searching for other galaxies that had brightened suddenly and without explanation over the past 20 or 30 years, wondering how many of those overlooked events might turn out to be other black holes caught in the very same act of waking up. And with newer, wider survey telescopes now coming online, chief among them the Vera Rubin Observatory in Chile, built specifically to photograph the entire visible sky over and over, night after night, for years on end. Many astronomers expect the number of known examples to grow substantially in the years just ahead. Ansky may not stay unique for very long. By around the spring of 2025, the combined efforts of 6 different instruments, the wide-field camera at Palomar that first caught the galaxy brightening, the Irosighter, and swift surveys that patiently confirmed the X-ray silence beforehand, the Chandra observation that pinned down the source, and the NICA and XMM Newton telescopes that characterized the eruptions themselves, had together recorded some 165 separate eruptions from Ansky. Since that first X-ray detection in February of the previous year, an extraordinary volume of data for a phenomenon that, only a handful of years earlier, had not been known to exist at all. Rarely does a single astronomical source demand quite this much coordinated attention from quite this many different corners of the field. Ground-based cameras and orbiting X-ray telescopes, European agencies and American ones, all quietly trained on the same small patch of sky in the constellation Virgo. The European Southern Observatory later pieced together images from several of these instruments into a single zooming sequence, gradually narrowing in from a wide view of the night sky all the way down to this one small, previously unremarkable galaxy, a fitting visual reminder of just how much attention this one quiet corner of Virgo had suddenly earned. Beyond the drama of any single galaxy, discoveries like this one matter for a much larger reason. Supermassive black holes sit at the center of nearly every galaxy of any real size, including our own, and yet scientists still do not fully understand how most of them first switched on back in the early history of the universe, or how often a black hole might power down for a long stretch only to reignite again later. Watching one galaxy do exactly that, in real time, close enough for today's instruments to study in detail, offers a rare working example of a process astronomers had mostly only been able to model on paper before now. Researchers studying this growing archive of bursts found themselves in an unusual position, one not often available in astronomy. Most cosmic processes unfold across timescales so vast that no human being could ever hope to witness real change happening. A star's life measured in billions of years, a galaxy's structure built up over an even longer stretch than that. Ansky offered something different, a black hole's behavior changing and evolving on a time scale a person could actually follow, month by month, almost season by season, simply by continuing to watch, checking new data as it arrived, the way a family might check in on a new arrival, curious what each week would bring, whether the rhythm had held steady or shifted again since the last look. Astronomers do not often get the chance to describe something like a black hole's early childhood, watching it change month to month the way a parent watches a child grow, never quite the same from one visit to the next. Ansky, quite unexpectedly, had given them exactly that, and watch they did. A renewed, sustained monitoring campaign using NISA ran from January of 2025 through January of 2026, a full year of careful, repeated observation of this same distant galaxy, far longer than the 54-day campaign described earlier in this story. What that year revealed was more striking still than anything the original 2024 discovery had shown. Across that year, NISA captured 23 separate eruptions from Ansky, including a remarkable, unbroken run of 19 consecutive bursts. More consecutive eruptions from a single source of this kind than had ever been recorded before. But the numbers themselves had shifted substantially since the very first characterization made only months earlier. The bursts, once roughly 1.5 days long, now lasted closer to 3 full days each, nearly double their original length, and the gap between bursts, which had first been measured at around 4.5 days back in the summer of 2024, had grown even further still, beginning that renewed year of observation at roughly 9.9 days between eruptions in January of 2025 and stretching smoothly, steadily, to roughly 13.5 days by the time the campaign concluded in January of 2026, an increase of well over a third within that single year alone. Sit with that for a moment. This was not a single dramatic jump from one measurement to the next. It was a slow, continuous drift unfolding across an entire year of careful watching, the timing between eruptions lengthening gradually the whole while. The way a person's breathing and heartbeat might slowly deepen and slow as they ease from a light doze into a far deeper sleep. Throughout all of this change in timing, the brightness and total energy released by each individual eruption stayed remarkably consistent, burst after burst, almost like a church bell that keeps ringing at exactly the same volume and the same tone, while the pauses between each toll of that bell grow steadily, noticeably longer. No other source of this kind, in all the years scientists had been studying this phenomenon, had ever shown anything like this continuous, measurable drift, and none of the sources described earlier in this story, settled as they were into their own long-established rhythms, had ever needed this kind of ongoing, open-ended attention. Ansky could not simply be measured once and filed away. It demanded to keep being watched, and researchers have made clear their intention to keep exactly that kind of watch going for as long as the rhythm keeps shifting. Astronomers do not yet have a fully settled explanation for why Ansky's rhythm keeps stretching this way, and the researchers, who have spent the most time with this data, have been careful to say so plainly rather than offer false certainty. Some suspect the still-forming disk of gas around this newly active black hole may simply still be settling, continuing to evolve in thickness or shape in ways that would naturally shift the timing of whatever process triggers each eruption. The way a pot of water on a stove takes longer to return to a rolling boil once it has grown a little deeper, or the way a newly poured concrete foundation keeps settling and shifting for months after it first sets, long before it finally becomes fully still. Others have proposed that the debris disk surrounding Ansky's black hole may be considerably larger than the disks theorized around older, more settled sources, capable of interacting with material orbiting much farther out than scientists had previously assumed possible for this phenomenon. One version of this idea suggests a smaller object, quite possibly the remains of a star, crossing through that larger disk not once but twice during each of its own orbits, striking the disk at a particular angle that produces a shock and a burst of X-ray light, each time it does. No observation has yet confirmed that a star was actually destroyed to create this arrangement, and researchers are careful to describe it as one candidate picture among others rather than a settled fact. If some version of this idea holds, then whatever object is doing the crossing could, in principle, allow the whole system to gradually widen its own path with each pass, lengthening its own cycle a little more every time around. Both ideas remain honest, reasoned possibilities rather than settled conclusions, offered by scientists who readily admit they do not yet have enough information to choose confidently between them. In fact, researchers studying Ansky have noted with a certain rueful honesty that there are currently more competing theoretical explanations circulating in the scientific literature than there is data available to properly test them, a rare and candid admission that the observations, extraordinary as they already are, have still outpaced our ability to fully explain them, and the story is not even finished being written. Just this past week, as this very episode was being prepared, a newly released study examining Ansky in even greater detail suggested the picture may be more complicated still than a simple tale of total silence followed by sudden awakening. This latest work raises the possibility that some faint, already ongoing feeding may have been taking place at this black hole even before its dramatic brightening in 2019, whether as a long fading remnant of an old, faint active phase that never fully died out, or as the lingering debris disk left behind by some disruption, event far older and far quieter than anything directly observed. This is very recent, very preliminary work, and it has not yet had the benefit of the years of scrutiny the rest of this story has already received. But it stands as a useful reminder that even the parts of this story that feel settled remain open to revision the moment better data arrives, and that the full history of this particular black hole may stretch back further than its dramatic public debut in 2019 ever suggested. Astronomers studying Ansky have already committed to continuing their watch in the months ahead, well aware that whatever new data arrives next could just as easily deepen this mystery as resolve it. What can be said with confidence tonight is this: a black hole that appeared to switch on within living memory has, within the span of only a few years, produced the most extreme rhythmic eruptions ever recorded from an object of its kind, and that rhythm itself has continued to change measurably month after month in a pattern nobody predicted in advance and nobody has yet fully explained. This alone sets Ansky apart from every other source described so far in this story, each of which, however strange its rhythm first seemed, eventually settled into a pattern steady enough to be measured once and trusted from then on. Scientists studying this phenomenon have even begun to wonder whether eruptions this powerful and this regular might one day be detectable by an entirely different kind of instrument altogether. A future space observatory called LISA, short for the Laser Interferometer Space Antenna, planned by the European Space Agency for launch sometime in the 2030s, designed to listen not for light at all, but for the faint ripples that such violent, repeating events might send outward through the very fabric of space itself. Ripples predicted by the same theories that first described black holes a century ago. Whether that future listening confirms what today's telescopes have already measured, or reveals something else again, Ansky has made one thing clear, beyond any reasonable doubt. Whatever mechanism lies behind these strange cosmic heartbeats is not fixed, not static, and not yet fully understood, and somewhere in that slowly stretching rhythm may lie a clue to understanding every other quiet, pulsing galaxy that came before it. A galaxy that spent 20 silent years giving away nothing at all has, in the years since, become one of the loudest, most closely watched objects in the entire X-ray sky, and it is still, tonight, in the middle of telling its story. Everything gathered so far in this story has pointed toward a single, quietly startling idea that a black hole's surroundings can behave less like the fixed, unchanging feature of a landscape and more like something with a genuine pulse of its own, capable of shifting, drifting, and changing shape over time. A tidy 9-hour heartbeat that never quite settled into perfect regularity. A second rhythm, looser and less predictable, hidden for decades inside data nobody had thought to look at twice. A whole small family of related rhythms, some fast, some slow, scattered across a handful of otherwise unremarkable galaxies. A newly waking black hole whose pulse kept stretching longer with each passing season of observation for reasons nobody has yet fully explained. But there is one more layer to this story, one that nobody watching the very first discovery could have anticipated, and it turns out to be the most quietly moving part of the whole account. These rhythms, it now appears, are not only capable of changing while they last. Some of them, in time, weaken. A few appear to stop altogether, and at least one of them, remarkably, has already stopped once and started again, right in the middle of the very story that first made it famous. That one is the very same galaxy where this whole story began. In the years following its initial 54-day discovery campaign, astronomers kept a careful, ongoing watch on that first heartbeat, the way you might continue checking in on an old friend long after the excitement of a first reunion has settled into something quieter and more familiar. For a good while, the rhythm held steady, essentially the same tidy 9-hour cycle first measured at the very start of this story. Then, some years later, something shifted. The quiet, steady glow between eruptions, the baseline hum beneath the rhythm, unexpectedly brightened on its own, rising back up after having spent years slowly fading, and as it did, the eruptions themselves grew irregular, uneven in strength, some barely rising above the background at all. And then, for a stretch of several months, they stopped. The heartbeat that had opened this entire story, the very first confirmed example of this kind of behavior anywhere in the universe, simply went quiet. Astronomers continued watching anyway, the way you might keep checking a phone line you suspect has gone dead, not quite ready to give up on it. And then, as that unusual brightening in the background glow gradually settled back down toward its earlier, familiar level, the eruptions returned. The same galaxy that had first taught scientists what a quasi-periodic eruption even was had in the years since, briefly fallen silent, and then, just as unexpectedly, found its rhythm again. Researchers studying this pause and recovery now believe the two events were connected, that the eruptions seemed to require the background glow to sit below a certain threshold of brightness in order to occur at all. An early hint that these rhythms may depend on delicate, specific conditions that can shift over time and, at least in this one case, shift back. It is worth sitting with how easily this could have gone unnoticed. Had astronomers grown tired of watching this one small galaxy during its quiet months, assuming the story had simply ended, they would have closed the book on it entirely wrong, mistaking a pause for a conclusion. The very galaxy that had seemed, for years, like the most reliably understood member of this entire family turned out to have a chapter of its own story that nobody had written down yet. This turned out not to be an isolated quirk, as the small community of researchers devoted to this phenomenon kept watching their handful of known sources for months and then years at a stretch. A genuine range of fates began to emerge. No two galaxies aging in quite the same way. One of the sources discovered through the systematic sky survey described earlier in this story, the slower, more patient one erupting roughly every 18.5 hours, weakened steadily over about 4 years of continued observation, its bursts growing fainter and fainter until, by the middle of a recent year, they had all but vanished from the reach of one telescope's instruments entirely. Only a more sensitive follow-up observation a few months later confirmed the heartbeat was, in fact, still there, just extraordinarily faint by then, roughly 10 times dimmer than its most recent visible bursts, and close to 100 times dimmer than the burst that had first announced its discovery years earlier. A neighboring source from that same survey told an even starker story. Its steady background glow, detected clearly in the survey's first 2 passes across that part of the sky, simply vanished afterward and was never seen again in that form, even as occasional faint, irregular flickers continued on top of wherever that glow used to be. A little like a torch, light that used to burn steadily through the night, suddenly going dark, while some other small, unpredictable light kept flickering faintly nearby. Astronomers also noticed that not every heartbeat in this family beats in quite the same shape to begin with, something worth understanding before considering how each one changes over time, and before assuming every rhythm described in this story looks identical up close. The very first source in this story, along with the fast, urgent one erupting every 2.5 hours, both tend to produce clean, isolated, evenly spaced bursts, one clear peak at a time, each one distinct from the last. Others, including the second confirmed heartbeat found buried in decades of overlooked archives, along with the slower, patient one that later weakened so dramatically, show a messier, more tangled shape instead. Individual bursts, sometimes overlapping or blending into one another before the rhythm settles again. Whether this difference in shape says anything about why some rhythms fade while others persist remains an open question, one more small thread in a story still very much being untangled. Scientists studying the source that later weakened so severely also turned to an entirely different kind of instrument to test their ideas: radio telescopes capable of detecting emission far beyond the reach of any X-ray observatory. Facilities called Meerkat, an array of dishes spread across the plains of South Africa, and the Very Large Array in New Mexico, both searched patiently for any radio signal coming from that same galaxy, checking whether the black hole might be doing anything more dramatic than its X-ray light alone suggested. Neither search found anything. That absence mattered. It helped rule out the possibility that a fully active, powerfully feeding black hole was hiding behind the scenes, suggesting instead that whatever was producing these rhythmic bursts required nothing more dramatic than the quieter, more modest kind of feeding already suspected throughout this story. Not every source has followed this same fading path, and the differences turn out to matter a great deal, offering scientists a natural experiment nobody had to design on purpose. The second confirmed heartbeat described earlier in this story, the one first traced back through 35 years of overlooked archival data, has remained detectable in every single observation made of it between the year 2000 and the early 2020s, more than 2 decades of quiet persistence without ever once dropping out of reach. And one particular source from the systematic sky survey, the fast, urgent one erupting every 2.5 hours, has proven remarkably steady across 3.5 years of careful monitoring. Its peak brightness, its temperature, and its overall energy output all remaining essentially unchanged the entire time. Give or take only the smallest, most marginal hint of its rhythm settling by perhaps 6 minutes over that entire stretch. A difference so small, it barely rises above the noise of the measurement itself. Even the subtle alternation between slightly longer and slightly shorter gaps, present when this source was first discovered, had quietly smoothed itself out by the time of these later observations. One more small wrinkle ironed out over time. If the very first heartbeat in this story could pause and resume, and if others could fade towards silence over a few short years, this particular source seemed determined to keep its rhythm going almost exactly as it always had, a steady presence in a family otherwise full of change. And yet even this apparent steadiness may not last forever. Researchers studying that same reliably steady source have pointed to an earlier, separately studied galaxy with a strikingly similar recurrence time and a similarly sized black hole, one that showed this same rhythmic behavior back in the middle of the 2000s. Only for careful follow-up observations 15 years later to find no trace of it left at all, the heartbeat having quietly faded out of existence sometime in between, without anyone catching the moment it happened. Because the steady source described here currently glows slightly brighter than that earlier galaxy did at a comparable stage, researchers modeling how these systems evolve over time have suggested its own particular clock may be running on a shorter schedule, evolving over roughly 5 years rather than 15, and have proposed that this same dependable 3.5-year steady heartbeat may itself fall silent sometime within the next 10 years. It is a strange thing to sit with, a specific, reasoned prediction that one of the steadiest rhythms known to modern astronomy carries something like an expiration date, quietly ticking down somewhere in the years just ahead of us, entirely unconnected to anything happening here on Earth. None of this should be mistaken for anything alarming. Nothing about a black hole's rhythm fading is a sign of danger to that galaxy or to anything nearby it, let alone to us, sitting here on Earth, hundreds of millions of light years away. It is simply what these systems appear to do over time, the way many natural processes run their course and settle, in their own way, into a different kind of quiet. What it does suggest, gently but unmistakably, is that these rhythms are not eternal fixtures of the universe, static curiosities that, once discovered, will simply persist unchanged for scientists to study indefinitely. They appear to have their own beginnings, their own middles, and in at least some cases, their own endings, unfolding on timescales short enough that a single research career, or even a single decade of careful watching, might reasonably expect to see one through, from its first flicker to its eventual quiet. There is a quieter, more statistical implication tucked inside all of this as well, one easy to overlook amid the drama of any single galaxy's story. If these rhythms can switch on, change, and switch off again within a span of years rather than centuries, then the small handful of examples known today almost certainly represents only a narrow slice of every galaxy that has ever done this or ever will. Countless other black holes may have pulsed this same way at some earlier point, long before any telescope capable of noticing existed, their rhythms beginning and ending entirely unrecorded, unwitnessed by anyone. Others may only begin this behavior decades or centuries from now, long after every instrument currently watching the sky has been replaced by something newer. The dozen or so confirmed examples gathered so far are not a complete census of this phenomenon across the universe. They are simply the ones happening to occur, or to have very recently occurred, during the narrow window of time in which humanity finally learned to look for them at all. This raises the deeper question that has been sitting patiently underneath this entire story from its very first heartbeat onward. What, precisely, is producing these rhythms in the first place, and why would something producing them ever need to begin or to end? The two competing explanations described earlier in this story, an object orbiting closely enough to graze the disk with each pass, or an instability arising entirely within the disk itself, each offer their own quiet answer to this question, though neither has yet been proven beyond reasonable doubt. Settling this question would do more than satisfy simple curiosity. It would tell scientists something fundamental about how ordinary a black hole's environment actually is, whether every one of these small, feeding black holes is quietly surrounded by captured companions, slowly working their way inward, or whether the disks themselves are simply less stable, less predictable places than anyone previously assumed, prone to their own kind of internal weather with no outside object required at all. If some version of the orbiting companion picture holds true, then what astronomers may actually be watching in every one of these galaxies is a small piece of an enormously slow and patient process that plays out over a vastly longer stretch of time than any single human observation could ever capture in full. In this picture, a much smaller object, perhaps the compact remains of a star or some other compact body captured long ago by the black hole's gravity, spirals inward around its much larger companion at an almost imperceptibly gradual pace, losing a little orbital energy with each pass, tightening its loop by the smallest of margins each time around, not unlike a coin set spinning on a table, circling faster and tighter as it slowly loses momentum, before it finally clatters flat and still. For an ordinary spinning coin, that whole process takes only a few seconds, the coin's edge blurring into a hum before it finally clatters flat and still against the tabletop. For an object slowly spiraling toward a black hole many hundreds of thousands or even millions of times heavier than our own sun, the equivalent process can stretch across many thousands or even millions of years, far longer than any civilization has yet existed to watch it unfold. If this picture is correct, then the rhythmic eruptions described throughout this story may represent only a brief, observable chapter within that much longer, quieter story, the specific stretch of time during which the smaller object's orbit happens to intersect the black hole's surrounding disk of gas closely enough to trigger a visible burst with each pass. Long before humans existed to notice, and long after we are gone, that same slow spiral may continue, mostly invisible, mostly silent to our instruments, only occasionally announcing itself, this dramatically, when the orbit lines up just right for however many centuries or millennia that alignment happens to hold. What we are catching, in other words, may not be the whole story of that small object's fate, but a brief, visible passage in the middle of it, the way overhearing a few minutes of a long conversation through an open window tells you something true and real about the people speaking without ever giving you the whole of what they said before you arrived or after you moved on. That same slow spiral, if it continues long enough and closely enough, is expected to end the same way for nearly every object of this kind eventually, drawn ever closer until it finally merges completely with the black hole it has been orbiting all along. When that final merger happens, theory predicts it should release a burst of gravitational waves, ripples in the fabric of space and time itself, spreading outward in every direction, the way the vibration from something heavy dropped upstairs can be felt trembling faintly through the floorboards of a house long after the sound itself has faded. Scientists have not yet directly detected gravitational waves from an event exactly like this, but a future space-based observatory, planned for launch sometime in the years ahead, built specifically to listen for exactly this kind of extremely slow, extremely long-lived spiral, may finally offer a second, entirely independent way to confirm what the X-ray light from these eruptions has only been able to suggest so far. Researchers have already begun discussing which of the galaxies described throughout this story might make the most promising targets for that future listening. Candidates whose rhythms seem most consistent with a genuine, ongoing spiral, rather than an instability confined to the disk alone. If that detection ever comes, scientists may finally be able to say with real confidence whether the rhythmic eruptions described throughout this story truly do trace back to a small object slowly spiraling to its end, or whether some other explanation altogether has been hiding in plain sight the entire time. The stakes of that answer reach well beyond this one small family of galaxies. If black holes of this modest size really do routinely capture and slowly consume smaller companions over enormously long stretches of time, then the handful of rhythmic eruptions gathered throughout this story may be only the visible tip of something far larger, a common, ordinary process playing out quietly around countless black holes that never happen to produce a visible rhythm at all, either because their companion's orbit never quite grazes a disk, or because no disk happens to be there to graze in the first place. What looks, for now, like a rare curiosity confined to a dozen unusual galaxies might eventually turn out to be a visible signature of something considerably more common, glimpsed only in the particular cases where the geometry happens to line up in our favor. It is worth pausing to notice just how young this entire field of study really is. A person alive today in their later years was already fully grown, already settled into a career and a family and a life of their own, before a single one of these rhythms had ever been detected by anyone, anywhere. Consider everything such a person has already watched arrive within a single lifetime. Television moving from a novelty into every living room, rockets first leaving the ground carrying human passengers, a footprint pressed into lunar dust and broadcast home for the world to see. This entire story, from its very first heartbeat to the newest, still unfolding chapter, arrived far more recently than any of that, tucked into just the last handful of years. The very first heartbeat in this story was found only a handful of years ago. Every single example gathered since, the second confirmed source rediscovered in decades of overlooked archival data, the family of sources found through systematic sky surveys, the tidal disruption that was watched for years before finally revealing its own hidden rhythm, and the newly awakening black hole whose pulse kept lengthening in front of astronomers' own instruments. All of it belongs to a period of scientific history shorter than a single generation. Entire careers in astronomy have been built and nearly finished without this phenomenon existing, as far as anyone knew, at all. Few areas of science offer a view this clear of a subject still being written in real time, this early in its own story, with so much of its basic shape still being worked out even as new examples continue to arrive, and even as some of the earliest examples quietly change or fade before researchers have finished making sense of them. There is something quietly remarkable in recognizing that a black hole an object defined for most of scientific history by what it refuses to give back, by the sheer, absolute silence of its event horizon, can also be the site of behavior, this changeable, this alive, with variation. The black hole itself, at the very center of every galaxy described throughout this story, remains exactly as dark and as silent as ever, giving up nothing, revealing nothing directly about its own interior. Nothing this story has uncovered changes that fundamental fact. The boundary itself has not softened. No signal has ever crossed back out from behind it, and none ever will. And yet the material caught in its gravity, spiraling, grazing, occasionally flaring with a rhythm scientists are still learning to read, behaves with all the variety and unpredictability of anything genuinely alive, beginning quietly, changing over time, sometimes fading, sometimes falling silent for a season, only to return, and in at least one predicted case, eventually stopping for good. A black hole cannot breathe, cannot age, cannot have a childhood or an old age in any way resembling a living creature's, and this story does not ask you to imagine that it does. But the disk of ordinary matter caught in its pull, the gas and debris still following the very ordinary rules of gravity and friction that govern falling water or a spinning coin here on Earth, can behave in ways that echo the shape of a life, a beginning, a season of change, and, for some, an end. The silence at the center holds. It is only the light circling just outside it that has, this whole time, been trying to tell us something. We happen to be alive at a particular moment in the history of this small, strange corner of astronomy, a moment when the instruments finally exist to catch these rhythms at all, and when enough of them have now been found, watched, and in some cases, watched all the way to their quiet ending, that scientists can finally begin asking not just whether this behavior is real, but what it means for how a black hole and its surroundings actually age over time. Ask nearly any question about the universe at large, how old it is, how it began, how it will end, and you are asking about timescales so vast that no human observation could ever hope to witness the answer directly. Only infer it patiently from indirect clues gathered over generations of careful work. This story has offered something different and rarer, a genuine cosmic process, however small and localized, that unfolds slowly enough to study in detail, yet quickly enough for a single dedicated researcher to watch its opening chapters and its closing ones within the span of an ordinary career. We did not choose this moment. We simply happened to be here for it, holding a small, incomplete, still growing record of galaxies that have taught us, one at a time, that even something as vast and as silent as a black hole can be surrounded by a rhythm with a genuine beginning, a genuine middle, and, it now seems clear, a genuine end. A century from now, whoever studies this same small family of galaxies will very likely know things about them that remain completely invisible to us tonight. Whether the drifting rhythm from the newly awakened black hole ever settled into a steady beat of its own, whether the steady, reliable heartbeat now predicted to fade within a decade truly did go quiet on schedule, whether the future listening for gravitational waves ever caught the final, decisive moment of one of these long, slow spirals reaching its end. We are not positioned at the end of this story. We are somewhere in its middle, listening as carefully as our instruments currently allow, aware that the next chapter is already being written somewhere out there, whether or not anyone is watching closely enough yet to notice. That, in the end, is the honest truth this story has been quietly building toward all along. We have learned to listen to something we once assumed had nothing at all to say, and everything that listening has revealed since. The tidy 9-hour pulse, the looser catch-your-breath rhythm, found hiding in decades of old data. The whole small family scattered across the sky. The newly waking heartbeat whose timing kept stretching in front of our instruments. And now, this quieter discovery that even the steadiest of these rhythms may not beat forever. All of it points toward the same simple, ungrand conclusion. What we are hearing is not a fixed signal from an unchanging object. It is something closer to a conversation still in progress, one we only recently learned existed, one we do not yet fully understand, and one that is still, this very night, being spoken somewhere out there in the dark, whether or not anyone happens to be listening. No triumphant answer waits at the end of this story, no final equation that resolves every open question raised along the way. What waits instead is simply a clearer, more honest picture than the one we started with, of a universe quieter than we once believed in some places, and considerably more restless than we ever imagined in others. Sleep now, listener. Somewhere far off, a small heart keeps its quiet rhythm still.